Welcome to the short video on option pricing and hedging with market friction using reinforcement learning. Let's start with the research motivation. Imagine John. John is an option market maker. John sold S&P 500 put options to clients who wanted downside protection. Now, he needs to hedge his delta exposure to remain delta neutral, but how does he do it accurately and efficiently? Currently, the Black-Scholes model underpins option pricing and hedging. It is a theoretical model that provides a closed-form solution to obtain the price and the delta, as seen on the left. It also makes several assumptions, with key ones such as constant volatility and a continuous time setting. Realistically, however, hedging is done in a discrete setting. Options cannot be hedged continuously, and even if it could, the profits would be eroded by transaction costs of rebalancing in infinitesimally small intervals taking place in a continuous time limit. Hence, the replication of an option is imperfect, giving rise to mishedging risk. Enter reinforcement learning. It has emerged as a promising approach to address some of these limitations. By framing option hedging as a sequential decision-making problem, reinforcement learning agents can learn optimal hedging strategies that consider various factors such as transaction costs, liquidity constraints, and stochastic volatility. We use the Q-Learning Black-Scholes model, aka QLBS, augmented with transaction cost and market impact cost models to get an optimal risk-adjusted pricing. These are the scope and goals of the research. 1. How does the delta profile differ between the QLBS and BS models? 2. How does the option pricing differ between the QLBS and BS models? 3. How does risk aversion affect option pricing in QLBS and BS models? 4. How does the inclusion of linear and or nonlinear transaction cost affect QLBS pricing and hedging? In the Black-Scholes model, the option price is equivalent to the expected value of the replicated portfolio. Over here in QLBS, a risk premium term is added to reflect the trader's risk aversion. The value of the portfolio can be adjusted as shown on the top right to reflect the different cost models. The option price can be obtained from the Markov decision process Q-value function. As Q-value seeks to maximize the cumulative discounted rewards, the option price seeks to minimize the replication cost and cumulative discounted variance of portfolio. Therefore, the option price is the negative of the Q-value. Data is generated by Monte Carlo simulations. 10,000 paths are created, rebalanced for 24 time steps. The results are promising. QLBS able to replicate the Black-Scholes method's price and hedge closely and accurately. Both the price and hedge converged eventually. In the chart on the right, the difference in option price represents the risk premium priced by the trader's risk aversion that we have seen earlier. The QLBS portfolio, which consists of the option and the underlying hedges, performed better than that of the Black-Scholes portfolio at the expiration of the option. The impacts of various cost models are also measured. At lower levels of epsilon, which is the transaction cost parameter, the linear and quadratic cost models have also similar impact and therefore similar option price. However, nonlinearity and divergence are observed at higher levels of epsilon. Eventually, it is found that the square root cost model provided the best risk-adjusted returns, which has a Sharpe ratio almost 50% higher than the next best option. Thank you.